Nothing made you. Let me say that again, because I know it sounds reckless, and I know it sounds like provocation, and I want you to understand that it is neither. Nothing made you. Not nothing in the casual sense, not the absence of effort or the lack of a plan. I mean nothing. The physical, measurable, staggeringly productive, nothing that preceded the existence of everything you have ever seen, touched, loved, or wondered about. The question I want to put before you tonight is the oldest question our species has ever formulated, and it is this: why is there something rather than nothing? And I want to warn you at the outset that we are not going to settle it. We are not going to walk out of this room with the answer tucked neatly under our arms, but we are going to do something that I think is far more important than settling it. We are going to understand, really understand, why the question is so much harder than you think it is, and why the partial answers we have found so far are among the most astonishing achievements in the entire history of human thought. I grew up in Brooklyn, Bensonhurst, to be specific, which is not a neighborhood known for producing cosmologists, though it has produced its share of characters who believe they understand the universe. My parents were garment workers. They did not sit around the kitchen table debating the vacuum energy of empty space. But my father did something that changed my life. He took me to the 1939 World's Fair. I was 4 years old. And then, a few years later, he took me to the American Museum of Natural History. And in that museum, I looked up at the stars projected onto the dome of the Hayden Planetarium, and something happened in my chest that I can only describe as a kind of magnificent terror. Those stars were real. They were out there. They did not care about me, and they did not need my permission to exist, and the sheer scale of them made every problem I had ever had seen not small but irrelevant in the most liberating possible way. And somewhere in the back of my young mind, a question formed that I did not yet have the vocabulary to express. Why are those stars there at all? Why is there a universe for them to live in? Why is there anything? Now, most people, when they hear that question, reach immediately for one of two answers. The first answer is God, an intelligence, a will, a creative force that decided there should be something and made it so. And the second answer is that the question is meaningless, that the universe simply is, and asking why is like asking what is north of the North Pole. Both of these responses have a long and distinguished philosophical heritage, and both of them, I want to suggest to you tonight, are premature. They are ways of closing a door that science has only just begun to open. And what is behind that door is far stranger, far more interesting, and far more humbling than either answer would suggest. Let me start where any honest investigation must start, with what we actually know. And what we know, with extraordinary precision, is that our universe had a beginning. Not a beginning in the mythological sense, not a creation story. A physical event that we can describe mathematically, that we can trace backward through the equations of general relativity, and that left behind evidence we can still detect with instruments built by human hands. Roughly 13.8 billion years ago, everything that now constitutes the observable universe, every galaxy, every star, every planet, every atom in your body and mine, was compressed into a state of unimaginable density and temperature. We call this the Big Bang, which is a terrible name. It was not big. It was inconceivably small. And it was not a bang. There was no space for it to bang into, and no time in which the banging could occur. What it was, as nearly as we can express it in human language, was the emergence of space and time themselves from a state that our current physics cannot fully describe. Now here is where it gets strange. Because when I say our current physics cannot fully describe the initial state, I do not mean that we are simply ignorant and need to work harder. I mean that the two greatest theories in the history of physics, general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of matter at the smallest scales. These two theories, each confirmed by experiment to a staggering degree of precision, are fundamentally incompatible with each other. They cannot both be right in the regime where the universe was born. General relativity says that at the moment of the Big Bang, the density of the universe was infinite, the curvature of space-time was infinite, the temperature was infinite. Infinite. That word should make you deeply uncomfortable, because in physics, infinity is not an answer. Infinity is a confession. It is the theory telling you that it has broken down, that it has been pushed beyond the domain where it has anything sensible to say. And quantum mechanics, which should in principle be able to rescue us from this infinity, has never been successfully merged with general relativity in a way that everyone agrees on. We have candidates, we have string theory, we have loop quantum gravity. We have ideas that are brilliant, and ideas that are half-baked, and ideas that may turn out to be the greatest intellectual achievements of the 21st century. But we do not have a finished theory of quantum gravity, which means that the very moment we most need our physics to work, the moment when the universe was born, is precisely the moment when our physics falls apart. I want you to sit with that for a second, because this is not a minor technical inconvenience. This is a crisis at the foundation of our understanding. We are asking why the universe exists, and our best tools snap in half the instant we point them at the question. And yet, and this is the part that fills me with a kind of ferocious optimism, we have still managed to learn an extraordinary amount about what happened just after that initial moment, in the first fractions of a second, when the universe was already expanding and cooling and beginning to take on the characteristics that would eventually produce stars and galaxies and planets and people who ask questions about why they exist. Let me walk you through it, because the details matter. In the first tiny fraction of a second, and I mean a fraction so small that writing it as a decimal would require more zeros after the decimal point than there are atoms in the observable universe. Something remarkable happened. The universe underwent a period of extraordinarily rapid expansion that we call inflation. This was not the ordinary expansion of the Big Bang. This was expansion at an exponential rate, driven by a form of energy that we believe was associated with a quantum field called the inflaton field. In a time span shorter than anything you can meaningfully imagine, the universe grew from something smaller than a proton to something larger than the entire observable universe is today. And when this inflationary period ended, when the inflaton field decayed and released its energy, that energy became the hot, dense plasma of particles and radiation that we recognize as the starting condition for the conventional Big Bang. Now, why does inflation matter for our question? It matters for a reason that I find genuinely breathtaking. Because inflation provides a mechanism, not a complete one, but a real and physical one, by which the universe could have arisen from what we might, with appropriate caveats, call nothing. Here is the key insight. In general relativity, gravitational energy is negative. This is not a metaphor. This is not a poetic way of speaking. The gravitational energy of a system is genuinely negative, and in a universe that is spatially flat, which our universe appears to be, to very high precision. The total energy of all the matter and radiation is almost exactly balanced by the total negative gravitational energy. The books very nearly balance to zero, and this opens up a possibility that would have seemed insane to any physicist before the 20th century. The total energy of the entire universe might be exactly zero. The universe might be, in energy terms, nothing at all. An elaborate rearrangement of zero into positive and negative parts that cancel out perfectly. I want you to think about what that means. It means that the universe did not require a deposit. It did not need energy to be injected from somewhere else. It could have arisen from a state of zero energy, because it still is a state of zero energy, just one that has been elaborately structured into galaxies and stars and you and me. The cosmologist Alan Guth, who first proposed the inflationary model, put it with characteristic pith. The universe, he said, might be the ultimate free lunch. And that phrase has a lightness to it that belies the depth of the idea. Because what Guth was really saying is that the conservation of energy, the most fundamental law in all of physics, the one we tattoo on the inside of every physicist's eyelids, does not forbid the creation of a universe from nothing. The accounting works. The books balance. There is no energy deficit that needs to be explained, but, and this is a very large but, this does not answer our question. It explains how the universe could have gotten started without violating the conservation of energy. It does not explain why it did get started. It does not explain the trigger. It does not explain why there was an inflaton field rather than no inflaton field, why there were quantum fields at all rather than no quantum fields, why there were laws of physics rather than no laws of physics. And this is where we arrive at the true frontier, the place where physics begins to shade into philosophy, and where honest scientists must be willing to say, I do not know. Let me tell you about a conversation I had once with a physicist. I will not name him, because he might not want to be associated with the degree of speculation involved, who said to me, over coffee, in a tone of absolute seriousness, Carl, the laws of physics are not just a description of what happens. They are the reason that anything happens. And I said to him, but where do the laws come from? And he looked at me with an expression that I can only describe as a mixture of irritation and genuine anguish. And he said, that is the question I have been trying not to think about for 30 years. And that, I think, is the honest position. That is where we actually are. We have a physical model. Inflation, the zero-energy universe, the quantum fluctuation that seeds structure. That is remarkably successful and remarkably well supported by evidence. We have measurements of the cosmic microwave background radiation, that ancient afterglow of the Big Bang, that confirm the predictions of inflation to extraordinary precision. We have observations of the large-scale structure of the universe, the distribution of galaxies, the pattern of density fluctuations. That match the inflationary prediction with a fidelity that still astonishes me every time I look at the data. The evidence is not speculative. The evidence is overwhelming. But the evidence tells us what happened. It does not tell us why. Now, there is a class of attempts to answer the why question that I want to address directly, because they come up in every public lecture I give, and they deserve a serious response. These are the arguments from fine-tuning, the observation. And it is a real observation, not a fabrication. That the fundamental constants of nature appear to be exquisitely calibrated to permit the existence of complex structures. Change the strength of the strong nuclear force by a few %, and atomic nuclei cannot hold together. Change the mass of the electron relative to the proton, and chemistry as we know it becomes impossible. Change the cosmological constant, the energy density of empty space, by a factor that is absurdly small, and the universe either collapses back on itself before any structure can form, or expands so rapidly that matter never clumps into galaxies. The universe appears to be balanced on a knife's edge, and we are here only because the balance is maintained with a precision that beggars description. This observation has led many thoughtful people to conclude that the universe must have been designed, that the fine-tuning is evidence of intentional calibration by an intelligence. And I want to be respectful of this conclusion, because the observation on which it rests is real, and the emotional response to it is understandable. But I also want to be honest with you, because honesty is the only thing I have to offer that is worth anything. The fine-tuning argument is not a scientific argument. It is a gap argument. It says, I see something I cannot explain. Therefore, I attribute it to a cause that is, by definition, beyond the reach of science. And gap arguments have a very poor track record in the history of human thought. Every gap that has ever been filled has been filled by a natural explanation, not a supernatural one. Every single time. This does not prove that every gap will be filled by a natural explanation, but it should give us pause before we rush to fill this particular gap with something that, by its very nature, cannot be tested, cannot be falsified, and cannot be investigated further. And there is, I should note, a competing explanation for the fine-tuning that is entirely within the framework of physics, even if it is not entirely within the framework of what we can currently test. This is the multiverse hypothesis, the idea that our observable universe is not the only one, that the inflationary process, once started, may never fully stop, that it produces an essentially infinite number of universes, each with different values of the fundamental constants, each unaware of the others. And in this vast landscape of possibilities, it is no surprise that at least one universe has constants compatible with the existence of observers who ask why their constants are so finely tuned. You do not marvel at winning the lottery if you know that an infinite number of tickets were sold. I have complex feelings about the multiverse. On the one hand, it arises naturally from our best theories. Eternal inflation is not something that was invented to solve the fine-tuning problem. It is a consequence of the mathematics of inflationary cosmology, and it was discovered to the surprise and occasional dismay of the physicists who discovered it. On the other hand, the other universes, if they exist, are causally disconnected from ours. We cannot observe them. We cannot send signals to them. We cannot, as far as we know, ever obtain direct evidence of their existence. And a theory that makes predictions we can never test occupies a troubled place in the landscape of science. It might be right. It might be the most correct and comprehensive description of reality ever formulated. But how would we know? And if we cannot know, what is the difference between a theory that is right and untestable and a theory that is simply a beautiful story? I do not have the answer to this, and I distrust anyone who claims to. But I will tell you what I believe, which is different from what I know, and I want to be clear about the distinction. I believe that the question of why the universe exists is a legitimate scientific question, not merely a philosophical one, and I believe that we will eventually find ways to address it that we cannot currently imagine. I believe this because the history of science is a history of expanding the domain of the answerable. Questions that were once considered permanently beyond the reach of human inquiry. The composition of stars, the age of the Earth, the origin of species, have been brought within the circle of scientific knowledge by the invention of new tools and new ideas. And I see no principled reason to exclude the origin of the universe from this circle, even if the tools required have not yet been invented. Let me tell you about something that gives me particular hope, because it connects the question of why the universe exists to a question that I have spent much of my career thinking about, which is the question of life. I am a biologist by training, in addition to whatever else I have become, and the origin of life is a question that shares a deep structural similarity with the origin of the universe. In both cases, we are asking how complexity arose from simplicity. In both cases, we are asking how order emerged from a state that, by any naive accounting, should have remained disordered. And in both cases, the answer turns out to involve a kind of creative instability. A tendency of the underlying system to generate new structures spontaneously, without direction, without intention, simply because the laws of nature permit it and the initial conditions happen to be right. In biology, we know how this works. Natural selection, operating on random variation over billions of years, produces organisms of staggering complexity and beauty from the simplest possible starting materials. No designer is required. No plan is needed. All that is required is a system that copies itself imperfectly and an environment that differentially rewards some imperfections over others. And the result, over time, is the entire biosphere. Every bird, every bacterium, every blue whale, every human being who has ever lived. All of it arising from chemistry. All of it emergent. All of it unplanned and yet, in retrospect, almost inevitable given the starting conditions and the laws. I wonder, and I want to be clear that this is speculation, not established science, whether the universe itself might be the product of a similar kind of process. Not natural selection in the biological sense, but some process by which the laws of physics themselves are not fixed and eternal but emergent, the product of some deeper dynamics that we do not yet understand. There are physicists who take this idea seriously. Lee Smolin has proposed a model of cosmological natural selection in which black holes give birth to new universes with slightly different physical constants, and the universes that produce the most black holes are the ones that proliferate most successfully. It is a beautiful idea. It may be completely wrong, but it represents the kind of thinking that I believe we need. Thinking that takes the question seriously enough to propose answers that are strange and testable and vulnerable to being proved wrong. And that is the key word, vulnerable. Any explanation for why the universe exists that cannot, in principle, be proved wrong is not an explanation. It is a statement of faith, and faith may be a fine thing in its proper domain, but it has no place in the investigation of nature. The universe does not owe us an explanation that makes us comfortable. It owes us nothing at all. Our job is to look at it clearly, describe it honestly, and follow the evidence wherever it leads, even when it leads to places that are strange and unsettling and far from any human intuition about how things ought to be. Let me talk about one more thing, because it bears directly on our question, and because it is the aspect of modern physics that I find most genuinely mysterious. This is the role of quantum mechanics in the origin of the universe. In quantum mechanics, the vacuum, empty space, the absence of everything, is not empty. It seethes with activity. Pairs of particles and antiparticles constantly pop into existence and annihilate each other, borrowing energy from the vacuum for the briefest of moments and then returning it. This is not a metaphor. This is not a picturesque way of describing something that is really classical and boring. This is a measured, confirmed, experimentally verified aspect of physical reality. The Casimir effect, in which two uncharged metal plates placed very close together are pushed toward each other by the pressure of virtual particles in the vacuum, was predicted in 1948 and measured in 1997, and the agreement between theory and experiment is exquisite. The vacuum, in other words, is not nothing. It is the lowest energy state of a quantum field, and it is alive with quantum fluctuations that are real and physical and measurable. And this has led a number of physicists, Alexander Vilenkin most prominently, to propose that the universe itself might have arisen as a quantum fluctuation from nothing, not from empty space, because space itself is something, not from a prior state of the universe, because time itself is something, from genuine, absolute, metaphysical nothing, no space, no time, no matter, no energy, no laws, just nothing. And then, through a process analogous to quantum tunneling, a tiny region of space-time flickered into existence, underwent inflation, and became the universe we observe. I want to be very careful here, because this idea is easy to caricature and easy to misunderstand. When Vilenkin says the universe came from nothing, he does not mean that he has explained away the mystery. He means that he has a mathematical model, a specific, calculable, well-defined mathematical model, in which the transition from nothing to something has a finite probability. It is not certain. It is not inevitable. It is not explained in the sense of being derived from something deeper. But it is possible, within the framework of quantum mechanics, and the probability is not zero. And in a scenario where quantum mechanics is the fundamental description of reality, and we have every reason to believe that it is, a non-zero probability is all that is required. Given enough of whatever it is that precedes time, even the improbable becomes inevitable. Now here is where it gets truly strange, because if the universe arose from a quantum fluctuation, then the laws of physics, the very laws that permitted the fluctuation, must in some sense have preceded the universe. They must have been there, waiting, in the nothing. And this raises a question that makes my head hurt every time I think about it, which is roughly once a day. What is the ontological status of the laws of physics? Are they descriptions of what happens, or are they the reason that things happen? Do they exist independently of the universe, like Platonic forms? Or do they come into existence along with the universe, like the rules of a game that are invented at the same time as the game itself? And if they exist independently of the universe, where do they exist? And what sustains them? I told you we would not settle this question tonight, and I meant it. But I want you to see the shape of the problem. I want you to understand that the question of why the universe exists is not a simple question dressed up in impressive language. It is a genuinely hard problem, perhaps the hardest problem. And it sits at the intersection of physics, mathematics, and philosophy in a way that no other question does. It forces us to confront the limits of our conceptual frameworks. It forces us to ask whether our very notions of cause and effect, of explanation and understanding, are adequate to the task. And it forces us to reckon with the possibility that the universe is, at its deepest level, stranger than we are capable of imagining. I have spent my life trying to communicate the beauty and the power of the scientific way of knowing. I have argued, in book after book and in hour after hour of television, that science is not just a body of knowledge but a way of thinking, a way of asking questions, testing answers, and being willing to change your mind when the evidence demands it. And I still believe all of that. But I have also come to believe something that my younger self might have resisted, which is that the universe has depths that our current science cannot plumb. Not because science is limited in principle, but because we are early. We are at the very beginning. The history of modern physics is 400 years old. The history of the universe is 13.8 billion years old. We have been doing this for an eye blink, and we have already learned things that would have been inconceivable to every generation that came before us. Imagine what we will know in another 400 years. Imagine what we will know in 1,000. The questions that defeat us now may seem elementary to our descendants, the way the motion of the planets, once the deepest mystery in all of natural philosophy, is now a homework problem for undergraduates. But I do not want to end on a note of comfortable optimism, because comfortable optimism is a form of laziness, and the universe does not reward laziness. I want to end with the discomfort. I want to end with the fact that right now, at this moment, the deepest question we can ask, why is there something rather than nothing, remains unanswered, not unanswerable, unanswered. We are not gods. We are primates with oversized brains who have figured out, through centuries of painstaking effort, how to ask the question properly. And asking the question properly is itself a monumental achievement. Because for most of human history, the question was buried under layers of mythology and assumption and premature certainty. Consider what it took to get here. It took Newton's invention of calculus and his discovery of the law of gravitation. It took Maxwell's unification of electricity and magnetism. It took Einstein's general relativity, which revealed that space and time are not a fixed stage on which events play out, but a dynamic participant in the drama, shaped by matter and energy and capable of being created and destroyed. It took Hubble's discovery that the universe is expanding. It took Gamow's prediction of the cosmic microwave background radiation and its subsequent detection by Penzias and Wilson. It took Guth's inflationary model and the observational triumph of the COBE and WMAP and Planck satellites. Each of these steps was hard-won. Each required genius and persistence and a willingness to be wrong. And each brought us closer to the point where the question of why the universe exists could be formulated not as a metaphysical lament, but as a scientific research program. And that is where we are. We are at the point where the question is precise enough to admit of investigation. We do not yet have the tools to answer it. We may not have the concepts. The answer may require a revolution in our understanding of physics as profound as the revolution that Einstein wrought, or the revolution that quantum mechanics wrought, or both. But the question is on the table, and it is a scientific question, and the fact that it is a scientific question, that we have earned the right to ask it as scientists and not merely as poets or theologians, is itself one of the great triumphs of the human mind. I want to say something about the cosmological constant, because it is the single most embarrassing number in all of physics, and it bears directly on our question. The cosmological constant is the energy density of empty space. Einstein introduced it into his equations in 1917 because he believed the universe was static, and he needed something to counterbalance the tendency of gravity to pull everything together. When Hubble discovered that the universe was expanding, Einstein called the cosmological constant his greatest blunder and discarded it. But it came back. In 1998, two independent teams of astronomers, Saul Perlmutter's group and the team led by Brian Schmidt and Adam Rees, discovered that the expansion of the universe is not just continuing, but accelerating. Something is pushing the universe apart, and the simplest explanation is that empty space itself has a small, positive energy density. The cosmological constant is real. But here is the problem. When you try to calculate the cosmological constant from quantum field theory, when you add up the contributions of all the quantum fields that we know exist, you get a number that is roughly 10 to the power of 120 times larger than the observed value. Let me say that again. The theoretical prediction is wrong by a factor of 10 to the 120th power. That is not a small error. That is the worst prediction in the entire history of science. It is so bad that it has its own name, the cosmological constant problem, and no one has solved it. We do not know why the cosmological constant is so small. We do not know why it is not zero. We do not know why it has the particular value it has. And the particular value it has is, as I mentioned earlier, exquisitely fine-tuned for the existence of structure in the universe. If it were even slightly larger, the universe would have blown itself apart before galaxies could form. If it were negative, the universe would have collapsed. It sits in a narrow window that permits the existence of complexity, and we have no explanation for why it sits there. This is the kind of problem that keeps physicists honest. Because you can talk all you like about the elegance of your theories and the beauty of your equations, but when your best prediction is wrong by 120 orders of magnitude, something fundamental is missing. Something deep about the nature of the vacuum, about the relationship between quantum mechanics and gravity, about the structure of space-time itself, is eluding us. And until we find it, our answer to the question of why the universe exists will remain, at best, radically incomplete. I want to mention one more thing before I close, because it connects everything I have been saying to a perspective that I think is essential, and that is too often missing from discussions of this kind. The question of why the universe exists is not just a question about physics. It is a question about us, about what kind of beings we are, and what kind of universe could produce beings that ask this question. This is sometimes called the anthropic observation, and it is frequently misunderstood. It is not an explanation. It does not tell you why the universe has the properties it has, but it does tell you something important about the relationship between the observer and the observed. It tells you that any universe you find yourself in must, by definition, be a universe capable of producing you. And this is not a trivial constraint. It eliminates vast regions of the possible parameter space. It means that the universe you observe is not a random sample from the space of all possible universes. It is a biased sample, biased by the requirement that it contain observers. Whether this is a deep insight or a tautology depends, I think, on your philosophical temperament. But I will tell you what I find most striking about it, which is this. The fact that the universe contains observers is itself a physical fact that requires explanation. The laws of physics did not have to permit the existence of consciousness. They did not have to allow chemistry, or biology, or brains. The fact that they do. The fact that the universe has produced, out of hydrogen gas and gravity and 4 billion years of Darwinian evolution, beings that can look back at the universe and ask why it exists. This is not a minor detail. This is one of the most remarkable facts about physical reality, and any complete answer to the question of why the universe exists must account for it. I want to leave you with one thought, one image. We are, all of us, made of atoms that were forged in the cores of stars that lived and died billions of years before the Earth was formed. The calcium in your bones, the iron in your blood, the carbon in every cell of your body, all of it was cooked inside a star. You are, in the most literal and physical and non-metaphorical sense, made of star stuff. You are the universe examining itself, asking about its own origin, wondering why it bothers to exist. And the fact that the universe has produced beings capable of asking why it exists is either the deepest clue we have about the nature of reality or the most magnificent coincidence in all of history. I do not know which it is, but I intend to keep asking. And I would be very disappointed in you if you did not do the same. There is a tendency, and I have fought against it my entire career, to treat the great questions of existence as if they belong to some specialized priesthood, as if only the credentialed, only the initiated, only the people with the right degrees and the right institutional affiliations are permitted to wrestle with them. This is nonsense. These questions belong to everyone. They belong to you. The universe did not check your credentials before it gave you consciousness. It did not ask whether you had studied physics or philosophy or theology before it made you capable of wonder. You are here. You are aware. You are asking the question. And that gives you standing. But standing is not the same as knowledge, and wonder is not the same as understanding. The difference between wonder and understanding is work. Hard, disciplined, often tedious work. The work of learning the mathematics. The work of understanding the experiments. The work of following the argument wherever it leads, even when it leads away from what you want to believe. And I will tell you something that I have learned over a lifetime of doing this work. The universe is always more interesting than your preconceptions about it. Every single time I have had to give up an idea I loved because the evidence contradicted it, what I found on the other side was better, stranger, more beautiful, more worthy of the effort it took to find it. The universe does not disappoint. It surprises. So here is where we stand. The universe exists. We do not know why. We have clues. The zero-energy universe, quantum fluctuations, inflation, the possibility of a multiverse. But we do not have an answer. And the question itself may require a revolution in physics that has not yet occurred, a framework that has not yet been imagined, a way of thinking that our current minds may not yet be equipped to produce. But we will produce it, or our children will, or their children, because this is what we do. This is what our species does. We look up at the sky and we refuse to be satisfied with easy answers, and we keep asking, keep probing, keep pushing the boundary of the known into the vast darkness of the unknown. And every time we push that boundary back, even by an inch, we learn something that changes what it means to be human. The question is not whether the universe has an explanation. The question is whether we are brave enough to keep looking for it, even when the looking is hard, even when the answers are strange, even when the universe stubbornly refuses to be what we expected it to be. I think we are. I have staked my life on the proposition that we are. And the only thing I ask of you tonight is that you leave this room a little less certain than you were when you walked in. A little more uncomfortable, a little more curious, a little more willing to sit with the magnificent strangeness of the fact that anything exists at all. Because that strangeness is not a problem to be solved. It is a gift. It is the beginning of every question worth asking. And we are only just getting started.